play a crucial role in switching between different probability distribution efficiently.
Thank you very much.
Okay.
Questions? Oh, please go ahead. Sorry.
Oh yeah, sorry. Yeah.
You wanted to thank your.
Can you hear me?
Okay, thank you, my advisors. Yeah, thank you.
Okay.
Any questions?
Yes.
Let's talk.
David, please.
What I'm curious about, can you talk a little bit about this constraint of the sum of the rate constants in a given reaction being fixed, like maybe in the context of this three-state model, why this is sort of a biophysically plausible constraint that you might face?
Yeah. The problem is that as you know, each reaction actually may be has different reactions or some small molecules. They are different species, so they often have different concentrations and are controlled by the upstream reactions. So, and the concentration must be limited, and this is just a simple assumption that the forward and the backward reaction rates is fixed. You can use any other linear constant on Kij or Kji, then you can get the same sort of conclusion. Yeah.
Okay, thanks.
Okay, one last question, Stephen, please.
Yeah, I was a bit curious about the nature of this geometric structure that you have. It looked like your protocols had some sort of jumps in them, which seems a little weird for Riemannian geometry. Can you say a bit more about like this metric tensor that you have?
Yeah, in the adiabatic limit where the total control time tau is very large, the jump step actually tends to 0 in inverse power law. So actually in the adiabatic limit, the discontinuity should vanish. But for the final control time tau, the discontinuity jump step exists.
But do you get these jumps in your metric tensor, or is this from a separate optimization? Like, does your metric give you this?
No, the final figure I show you is from the numerical solution, which the control time tau is a final value. Yeah.
Okay,
in
cool.
theory, yeah. Thank you.
Yeah, that's okay. That makes a lot of sense. Thank you. Very nice talk.
Thank you.
Thank you very much. We are out of time, so we should move ahead. And the next talk will be by Davide Santolin, and he will tell us about dissipative metastability. Please share a slide.
Okay. So can you hear me?
Yes.
Okay, and can you see the slide now?
Yes, it's still not in the presenter mode.
Yeah, okay. Now should be in presenter mode.
You're good to go.
Okay. So, hello everyone. I am Davide Santolin, PhD student from the University of Padua. And today I'm going to talk about dissipative metastability using a stochastic thermodynamic approach. So before moving to non-equilibrium, I would like to recall a few concepts about equilibrium metastability, which is usually associated to the idea of a system evolving on an energy landscape with the minima enclosed by high energetic barriers. So everything is conservative, the dynamics is detail balance, and the transition rate between metastable states is governed by the famous Arrhenius law. So when we are out of equilibrium, instead, we cannot rely on this idea of systems evolving on an energy landscape. This is due to the fact that we have non-conservative forces continuously dissipating and breaking detail balance. In this sense, we have no results akin to Arrhenius in terms of equalities connecting the dynamics to the system energetics. So what we try to do is to fill this gap by deriving inequalities that connect these two realms. So as a starting point, we first focus on the simplest example of metastable states, which is dissipative fixed point. And we did it in the framework of overdamped diffusion processes in weak noise limit, where the weak noise is represented by this epsilon to 0 limit in the noise term that you can see. And this lowercase u is the drift, which if is nonlinear, we know the system can display metastability. And the system is actually metastable when it shows stable fixed point separated by a saddle. And in presence of weak noise, we can observe in the long time limit a transition between a metastable state. And for us, a metastable state will be the basin of attraction of a stable fixed point. Reason for which a transition will be a path connecting a stable fixed point to a saddle, because what comes after is just a deterministic relaxation into another metastable state. Things get complicated when in the drift we have some terms breaking detail balance. In that case, in the long time limit, we won't reach equilibrium. But given the framework of weak noise, we know that our stationary distribution that we will reach in the long time limit, we will have the form of a WKB distribution governed by this quantity, ISS, which is called quasi-potential. That is an object that plays the role of the conservative potential in the equilibrium case, let's say. So in this framework of large deviation theory, Friedling and Wenzel derived their expression for the transition rate, which is formally equivalent to the Arrhenius formula. There is a dependence on the quasi-potential barrier, but this formula has no clear thermodynamic interpretation, and also the quasi-potential is hard to be determined. So let's see what we can do in terms of deriving some thermodynamic bound on this quantity, on this transition rate. So our idea is the fact that the escape rate is controlled by dissipation along the two most probable trajectories connecting a stable fixed point to a saddle, that are the relaxation trajectory and the instanton. Because the point is that when we are out of equilibrium, the tail balance is broken. And so the existing time reversal symmetry that we would observe at equilibrium between instanton and relaxation, that are one the time reversal of the other, is lost. And we can see it by deriving the Hamilton equation governing our system dynamics and playing a bit with this drift field decomposition, in which the drift can be rewritten in terms of the gradient of the quasi-potential and this V, that is the probability velocity, an object related to the current that we have at stationarity. And we get this expression in which, depending on the sign that we take, we have the instanton or the relaxation, and we can no longer map one trajectory into the other by simply reversing the time. So, okay, we have these two trajectories. Let's see what we can do in terms of thermodynamic with these two trajectories. So the idea is that, again, with the drift field decomposition, we can split the entropy production in two terms, the adiabatic and the non-adiabatic contribution. And so what we observe is that if we take the adiabatic contribution, no matter the kind of trajectory we are considering, so the instanton or the relaxation, this quantity will be always positive because it's quadratic in these velocities. While the non-adiabatic term will be actually the quasi-potential barrier, but changing sign depending which one trajectory we are considering. And so putting these things together, we can relate it with the expression by Friedling and Wenzel and build this chain of inequalities in which the logarithm of the transition rate in this weak noise limit is controlled from above by the dissipation along the instanton and from below by minus the dissipation along the relaxation. So we tested our bound by using this minimal model of a bistable potential under a rotational flow, that is our non-conservative force. We looked at the bound at different intensities of non-conservative forces, that is represented by this gamma parameter here. And so For each intensities of the non-conservative force, we derived the instanton and the relaxation. We integrated the quantities of interest, and we derived this bound, which we observe is tight when we are close to equilibrium, because the time reversal, the mapping between the two trajectories, the instanton and the relaxation, starts to be recovered. Okay, so much for time-independent attractors. Then we wanted to study time-dependent attractors, more complicated and more pure non-equilibrium, let's say, metastable states, which are limit cycles. We know that in a deterministic framework, limit cycles are stable periodic orbit. But when we add some weak noise, we have quasi-periodic stochastic path that shows the correlation in the long time limit, governed by this characteristic time that is tau c. That is called correlation time. So for this system, there was this conjecture bound telling you that the number of coherent oscillations that a system with a limit cycle can display, that is the product of the mean oscillation frequency times the correlation time, is controlled by the mean entropy production per cycle divided by 2 pi. So this is an interesting bound because it tells you about the trade-off that a real oscillating system shows between its precision and the energy that is dissipating. And it is useful to study, for instance, real electronic clocks. So that could be an example, this minimal circuit that is the ring oscillator, a set of an odd number of inverters put in series like this. And so the hard part is actually determining the correlation time. You can do it by applying Floquet theory to the Hamilton equation describing our dynamics, and you get this known result for the correlation time. But here you see the diffusion matrix and this object zeta, which is actually the hard part to be determined. This zeta is the leading Floquet mode, an object that tells you about the asymptotic stability of the system. But we know that this zeta has to satisfy this Biot-normality condition with the drift. And so our intuition was that if the system was 1D, we could know in closed form this zeta is the reciprocal of the drift. So we decided to project the dynamics along the limit cycle and treat it as a 1D system, actually. And we derived the bound in closed forms for this tangent dynamics. And then we wanted to weaken the bound in order to connect these one-dimensional quantities with the true quantities of interest. So we started by weakening the dissipation side, the right-hand side, and we showed that the dissipation in the 1D system is underestimating the dissipation in the full-dimensional system. You do it by playing with Cauchy-Schwarz inequalities. And then we considered also the fact that our Langevin dynamics could be the result of some kind of Van Kampen expansion of a Markov-Jan process. And so the true microscopic entropy would be, entropy production would be underestimated in that case. And so we end up with this hierarchy of entropy productions. The hard part is now the left-hand side. And to proceed analytically, we have to do some assumptions on the analytic form of the diffusion matrix. And we've been able to derive everything analytically for systems in which the diffusion matrix is proportional to the identity. For more complicated systems, instead, we had analytic results only close to a Hopf bifurcation. For the rest, we had to rely on numerical simulation to confirm the bound. So we took 3 models as a reference for the different kind of diffusion matrices, the bistable potential with the shear flow that I used before, for systems that are with a diffusion matrix proportional to the identity, the ring oscillator for system that has a diagonal in the diffusion matrix, and for the most general case, instead, we took the Brussellator as a reference. And for all of them, arbitrarily far from equilibrium, we managed to prove the same bound. Here there are all different fashions of the same bound. And so we verified the fact that the number of coherent oscillation is actually controlled by the entropy produced per cycle. And with this, I can conclude my presentation, and I thank you for the attention. I would like to thank my supervisor, Gianmaria Falasco, and all the other co-authors, Noel Freitas and Massimiliano Esposito, and thank the organizer for giving me the opportunity to present my work.